So problem 29.11 asks us to find the current in the loop. And the loop in question has a magnetic field in the center of 2.40 milliteslas and a diameter of 0.60 centimeters. So you can see from the picture we have a loop. It is an ideal loop for this problem, and that has some current I going in it, and a diameter of 0.6 centimeters. So our book gives us essentially the equation for what that magnetic field strength is at the center of a coil, which is the U naught over 2 times N times I over R. That U naught is just that constant. I believe it's the permeativity constant. And N is the number of loops. So in this case, for us, it's just going to be 1. And the other stuff is, for example, R is the radius, and I is the current, which is what we're wanting to solve for. So all we have to do in order to solve for the current is rearrange this equation, because we actually have all the information we need. So doing that, we get an equation that basically states that the magnitude of the magnetic field at the center times 2R over that constant times N equals the current. So once you plug in the numbers for that, notably I changed my units right at the beginning, but that's always going to be, you could do it now, like in the solving part, but just make sure to do it to get the right answer. We get an answer of about 11.5 amperes for the current going around this loop. So that's part A. Part B states that a long straight wire carries some current, the same current as an A, which is 11.5. At what distance from the wire is the magnetic field 2.40 milliteslas, which once again is the same value we had in A. So the equation for this, once again, is given in the book. It's that constant over 2 pi times current over R. So what we're wanting to solve for is R, and we have everything we need, therefore, to do that. So you can see in my drawing, we're treating this like a infinitely long wire, essentially, since our problem grants us that it's a long straight wire. And with the direction I made my current, you can kind of see how the magnetic field circulates around our wire. But that's just extra information. We can go ahead and just rearrange this equation and solve. So when you rearrange for R, you get R equals that constant times I over 2 pi times the magnetic field of the wire. And plugging in our values, we get a distance of 9.6 times 10 to the negative 4th meters. So that's the answer for part B. I think overall this problem is pretty simple as long as you know how to refer back to those equations. But the thing that can be kind of tricky, I guess, in part A is like making sure your units are correct. But other than that, it's not too bad. Yeah, that's pretty much it. Thank you for listening.